The carbonyl group and the multiple hydroxy groups present in monosaccharides contribute to its chemical properties. One such property is de Bruijn-van Ekenstein transformation. It is a series of tautomerization in basic solution that leads to isomerization, often for several days. Glucose may isomerize in this basic solution to mannose and fructose. Recall that this alpha hydrogen is acidic and can be taken by a base, which in the process would form this ketone component or facilitate an inversion of configuration. Hence, D-glucose may isomerize to D-fructose and D-mannose. The hydroxy groups of sugars can also react to form ethers. These ethers may be formed by Williamson synthesis. Benzyl ethers can be cleaved by hydrogenolysis. Exhaustive methylation can be carried out using dimethyl sulfate or iodomethane. Here, a base can facilitate the SN2 attack of the oxygen to dimethyl sulfate. Exhaustive methylation is used in preparation for structural analysis of oligosaccharides and polysaccharides. The hydroxy groups of sugars also allow ester formation. Here we use acid chloride or acid anhydride in weak base. Esters are cleaved by basic treatment. This type of reaction will be described in the next topic. Given that monosaccharides have multiple hydroxy groups, two hydroxy groups in carbohydrates in proper orientations can react to form cyclic acetals. For example, this methyl glucoside may react with benzaldehyde in the presence of an acid to form this cyclic acetal. This is a 6-membered cyclic acetal. Different oxidation levels can exist for carbohydrates. They may be alditol, aldose, ketose, aldonic acid, the case wherein the aldehyde group becomes a carboxyl group, uronic acid, in the case wherein the terminal CH2OH group becomes a carboxylic acid group, and aldaric acid, wherein the terminal groups are both carboxylic acid groups. Tests were developed to identify the reducing property of sugars. The bluish Benedict's reagent, or basic cupric citrate, and Fehling's solution, the basic cupric tartrate, both give a brick red cuprous oxide with aldoses and ketoses. In the process, this aldehyde group becomes a carboxylic acid, and the oxidation state of copper is reduced from +2 to +1. Tollens solution also reacts with aldoses and ketoses, giving a silver mirror. Carbohydrates with hemiacetals are called reducing sugars, and those with only acetals are non-reducing sugars. Hemiacetals are reducing sugars because they are in equilibrium with the open chain form, which becomes oxidized. Bromine water selectively converts aldehydes to carboxylic acids, that is, from aldose to aldonic acid. Nitric acid oxidation, by the use of dilute nitric acid, oxidizes both the aldehyde and primary hydroxy groups of an aldose to an aldaric acid. Because sugars have multiple contiguous hydroxy groups, periodic oxidations can be carried out by the use of periodic acid. In this case, the terminal CH2OH becomes formaldehyde. The internal CHOH and aldehyde carbonyl become formic acid. The ketone carbonyl becomes carbon dioxide. For example, this aldose is expected to form 4 equivalents of formic acid and 1 equivalent of formaldehyde in the presence of periodic acid. Periodate oxidations require vicinal OH groups or OH group adjacent to a carbonyl. Otherwise, no cleavage of the CC bond occurs. Periodic acid can also be used to identify the type of monosaccharide. 1 equivalent of periodic acid is required to cleave a CC bond. For the case of this aldose, there are 1, 2, 3, 4 CC bonds, hence 4 equivalents of periodic acid is required. Aldoses and ketoses are reduced to alditols by treatment with sodium borohydride or metal-catalyzed hydrogenation, such as this one. Three equivalents of phenylhydrazine reacts with aldoses or ketoses to yield phenyloxazones. Phenyloxazones readily crystallize and they can be separated quite easily. D-glucose and D-mannose give the same oxazones. Take note that glucose and mannose only differ at the configuration at C2. Hence, their oxazones are expected to be identical. Sugars that differ in configuration at only one chirality center are called epimers. D-glucose and D-mannose are epimers. The length of monosaccharides can be increased by using Kiliani-Fischer synthesis. This is a method for extension of the carbon chain of aldoses through the formation of epimeric cyanohydrins. The reaction of prussic acid with this monosaccharide can generate this cyanohydrin and its diastereomer. Hydrolysis of the cyano group can lead to an aldonic acid. Dehydration of this aldonic acid can form the aldonolactone, and reduction of this lactone can give an aldose which is longer by 1 carbon compared to the starting material. An update of this procedure uses hydrogen in the presence of palladium and barium sulfate. This update reduces the number of steps in this synthesis. The product of this transformation is D-erythrose. If the diastereomer of this cyanohydrin is utilized, D-threose is expected. If Kiliani-Fischer synthesis increases the length of the aldose chain by 1 carbon atom, rough degradation is the reverse. It allows the shortening of the aldose chain by 1 carbon atom. This involves oxidation of the aldose to aldonic acid by bromine water, followed by oxidative decarboxylation to the next lower aldose. Here, D-mannose, an aldohexose, becomes D-arabinose, an aldopentose.